Great. Okay. Thank you everyone for coming to the Rubin Science Assembly today. So I'm the host. I'm Christina Williams. I'm at Noir Lab. I'm a community science team member, and I'm going to demonstrate today a functionality of the Rubin science platform called the image cutout service. So that's what we're going to do today. First, I'll just show the agenda here. So in the first couple minutes, we'll sort of go over some of the announcements um, of ongoing activities. And then in a couple minutes, I'll start the tutorial. So for those of you that are getting that are interested in which tutorial this is, you can see the file name here. It's on our Rubin DP0 tutorial notebooks repo, and it's tutorial DP 0.2 tutorial 13A called image cutout side demo. So it's kind of a long tutorial, so I'm going to try to finish sometime around 9:45 so that there's time for questions, but you can also raise your hand in the middle of the presentation and ask questions whenever you have them. And then we'll have some time for questions at the end. So here's the link for the tutorial notebooks repo if you need to find it. And so I'll just go through some announcements briefly. So we have the Rubin Community Workshop coming up, the Project and Community Workshop for 2024, which is July 22nd through the 26th, and it's at Slack, and there's also virtual attendance available. And so the registration is open, but it will close at 250 in-person participants. So if you're interested to go, it would be good to register soon. And also to remind everyone, we're having a Rubin Data Academy from June 17th through the 21st. So this is formerly known as the DP0 Virtual Summer School, which we also ran last summer. And this is going to be a 4-day long intensive series of presentations and tutorials and co-working sessions. And we're especially welcoming to students, and there's no prior experience or preparation is needed. So if you're interested in doing this, please register. The link is here, and maybe someone can post it in the chat so that people can register. And I think it will be a very great way to get sort of immersed in how to use the Rubin Science platform and how to use the Rubin data sets. So we also want to announce that we have Spanish language tutorials now available on the repo. So you can read more about that on this community forum post. And then we have 2 workshops coming up, one in Chile at the La Serena, so LSST will be at a meeting there, and then also at LSST at Europe 6 in La Palma in Spain. And so those things are coming up if people are interested in attending those. And just a quick look forward at what's up and coming with the Rubin Science Assemblies in the next few weeks. So today I'm going to talk about the image cutout service. Next week is our question and answer drop-in session with the Rubin staff. And so this is also going to be a co-working time if you want to work with others or get help solving problems or various things. So it's an open session for that, for drop-in. And then in 2 weeks, we're having another tutorial presentation, how to do synthetic source injection by Jeff Carlin. So we have exciting things up and coming. Does anyone have any questions about the announcements before I proceed to the tutorial? All right, looks like no. So I will now open a new notebook session on the Rubin Science platform. So we're going to data.lsst.cloud. And if you can log in on the right if you're not logged in yet. And I'm going to click on the notebooks aspect in the middle here. And this notebook requires some fairly large amount of image display, so I recommend opening it with a medium container. I already have this open, so I guess it didn't give me the option to check. So if you're new to the Rubin Science platform, you want to go to the place where you have tutorial notebooks set up to mirror to the tutorial notebooks repo on GitHub. And the tutorial that we're going to do today is DP02_13A, the image cutout science demo. Okay, so just a little bit of overview about image cutouts. So probably in earlier sessions on the Rubin science assemblies, you've heard about the images that are stored in the Rubin database, and they're in fairly large chunks. So both the CalX files and the deep coad files are very large sections in the database. But for pretty much almost any science application, I think it's very useful to be able to visually inspect images of individual sources or regions of the sky. And so it's sort of not very efficient to transfer over these large images. And so we have this image cutout tool, which serves the purpose of being able to visually inspect individual sources with much less data transfer involved. So I'm going to demonstrate how this thing works in this notebook. And so I think there's a large number of applications, but I'll just overview a few science applications that may be, make use of the image cutout tool. And so the way that this service works is it enables you to retrieve a small image out of one of the bigger LSST image cutouts. And the cutout is performed on the server side. So you're not transferring over these huge images. You're just defining a small image region, sending it to the server. The server is doing the cutout for you and then sending you the small cutout. And so the amount of data transferred from one direction to the other is much smaller. And that can make this much more efficient and faster. And the way the service that this uses is from the International Virtual Observatory Alliance, or IVOA. And this provides, it's sort of a industry standard that LSST also complies with, so that it interfaces in the same way that it works with other virtual observatory standards. So I'll just get started then. So here we have some introductory blurbs here in case you're interested to learn more of the details. There's some links here that give some more of the technical details of how this process works. So if you're interested, you can read those. I'm going to sort of skip over them, but I'm happy to answer questions about them. So we'll load up all of these Python packages, and we're going to define some defaults for plotting here, and then we're going to create some environment variables. So in this notebook, we're going to create some cutouts, and we're going to store those FITS files on the Rubin Science platform. And so this is just going to define where that is in your home directory. At the end of the notebook, we're going to delete all of the images, but you will have to delete the temp directory yourself because we weren't able to automate it in the notebook. Okay, so we're going to define some functions that are going to get used. So this plot image function is simply shorthand for plotting some of the images that we're going to create. So that's what plot image is. We're going to define that. Make image cutout is a wrapper function that is going to generate these cutouts for us. So in the first section of this notebook, I'm going to first show how this procedure works. But then in later parts, once I've explained all of the procedures of how you do this, you can just call this wrapper function and it will do all of the image cutout definitions for you. So we're going to compile that. And then at the end of the notebook, hopefully I can get to it, we have some other sort of cool ways to visualize some of the cutouts using transients. And so we have some functions here: warp image, get min max XY, and make GIF, that will help us to make those visualizations later. So I won't go through all of the details of those. All right, so the first step is we have to open the TAP service, and the TAP service is going to help us to define the data set that we need to access from the database when we're making these cutouts. So I'm initiating the TAP service. And for this first example, I'm going to pick a part of the sky that has a really nice galaxy cluster. And you may have seen this galaxy cluster in earlier notebooks. So we have the RA and DEC coordinates of the galaxy cluster. And I'm going to use the TAP service to figure out which deep coad patch and tract this galaxy cluster sits in. So that's what this query is doing. And we end up with a patch and tract that we can use to define the data ID. And the data ID is just a list of it's a structure containing the filter that we're interested in. So I've just specified the I-band here, the patch and tract of this galaxy, of the deep coad that contains this galaxy cluster. And this data ID is what we're going to use to figure out where on the server the image is sitting, and then we're going to send those parameters to the image cutout service so we can go perform this cutout on that patch and tract image. All right, so now, now that we know what the data ID is, we have to use this table collection called IVOA. So IVOA was the virtual observatory service that I was talking about before, and it holds the metadata for these DP 0.2 data sets. So we're going to use the TAP service to locate the images of this data ID using the obs core table. So I'm going to run that query, and this is going to return this table. So this is showing us basically the URL. So the important part of this here is the access URL column, and that holds a URL that is contained. It's the location of where the patch and tract for this data ID data set is. So here you can see some of the other things about it. So we requested the LSST I-band, the LSST patch and tract that contained the galaxy cluster here. This tells you it's a deep coad, and then it shows you the RA and DEC of the patch and tract. So this access URL is what we need in order to specify to the cutout service where the location of the data set is that we need to cut out of. So we're going to extract this. This is called a data link, and we're going to extract this from the query result here. So this is retrieving the data link from the result of the TAP query, and this is telling us that the data link status is fine. So it exists, and we're ready to use it for a cutout. So now this last part of section 2. I guess this is 2.1, 2.2. We're going to run this SOTA query. So SOTA is the name of the cutout service that we're going to use, and we're going to use the data link to request the image. So this is now we've defined using the SOTA query that this is the image that we're going to use, and it uses this data link to tell to say where the remote location of this image is. All right, so now that we've identified which image we need a cutout of, and we have the data link for that image, we are going to define the cutout region that we need to use. So there's a few different ways to define the cutout. So I'm going to demonstrate first a simple way to define the cutout, which is to say we want an RA and DEC center of, we specify the RA and DEC center, and then we can specify the cutout by a circle of radius R. And so the cutout will be a square, but it's the square that's sort of subtended by this circle that you've defined with a certain radius. And all right, so I'm going to do that here. And so this is going to take a minute. Looks like it takes about 12 seconds. All right, so this is now, we've requested a circle cutout from that data, the image contained in that data link. And we requested an image that's 0.05 degrees in radius. And then we called the cutout service to save a cutout of that image. So we've saved that here as SOTA cutout circle.fits. So then you can open this cutout. The cutout's now remotely stored on your Rubin Science platform, and you can open this using the plot image function we defined earlier. And so here's the galaxy cluster. So this is a small chunk of the patch and tract, but we've managed to retrieve just a small part of it. We didn't have to wait for the full transfer time for the entire patch and tract. And then we didn't, it's easier to visually inspect this way. Does anyone have any questions about that? All right, great. Feel free to interrupt me. I know this is potentially can be confusing. Okay, so I showed you how to do this with a circle, but you can also use a polygon to define the cutout shape. So this requires a lot more parameters because you then have to specify the corners of the polygon. So it says polygon, but the only options are to get square or rectangular shapes out of the cutout service. But this is nice because whereas the circle forces you to have a cutout that is square shaped because the radius specifies the subtended circle specifies what the cutout shape is. It's always going to be a square, but using the polygon, you can instead specify rectangular shapes and rather than shapes that have the same edge on both sides. So here I've shown an example of how to, so we've started a new SOTA query for the same data link. So this is the same patch and tract that we defined already, but now we're going to create a new cutout that has a different shape. So we're going to use a more elongated shape that is, instead of 0.05 degrees in radius, it's going to have 0.01 degrees in one direction and 0.03 degrees in the other direction. So here's the command. So we're going to run that. And it's going to give us this rectangular. Sorry, I have the notebook loaded already in a different RSP, and it seems to have stored the images, so they're already here. But you'll see why I did this later. Okay, there's a message in the chat. Can you add more vertices to create a pentagon? No, you can't. Although that would be cool. Right now, it only supports rectangular shapes, so it has all the angles have to be 90 degrees. Which is why the circle cutout is kind of confusing because it's not giving you a circle, but it's sort of how you define the rectangle that you get returned. So here you can see when you that you get a rectangular cutout instead of a symmetrically square cutout. All right, so one thing that is important to note is that so as you go to higher and higher latitudes or declinations, the distance in the RA direction changes by cosine of the declination. So as you go to very high declination, the distance between different degrees in RA is actually on the sky is actually much smaller. And so while the circle cutout accounts for this, the polygon does not by default account for this. And so if you want to get on sky distances in the RA direction, you need to make sure that you factor in this cosine declination factor. So here I've just demonstrated how to do that. So for the RA direction, you have to divide by cosine of the declination. So I just have a different example where you do that, and it comes up with a slightly different scale in the RA direction because of the cosine factor that's not factored in the polygon. All right, so we're running that. It's taking a minute. All right. So anyway, that's an important thing to keep in mind. All right, so I've sort of demonstrated now, this is the end of the first phase of the tutorial where we've gone through the different steps that is required. We have to first define the image we want to retrieve. We need to query where in the database that image lives so that we can specify the data link to that. And then we define the cutout shape that will be sort of extracted from the parent image on the server side and sent to the Rubin Science platform in your directory. So that's sort of the overall procedure. Does anyone have any questions about all that stuff? And then if not, I'll proceed into some science demos of how this can be a useful procedure.
I have one question.
Yeah.
Is there the image size limit per transfer or number of images?
Oh, you mean the number of images?
Number of images and the size of the images.
So the number of images, right now you can only extract one at a time. I'm not sure if there's going to be a capability to send it a full list, but basically you have to retrieve each cutout individually, to my knowledge, at the moment. But I think you could, in principle, just even if you just wanted to use the cutout service to return the entire image, I don't think there's anything stopping you from doing that. I don't think so. I don't think there's a size limit. But if somebody knows more about that than I do, please let us know. Okay. Anyway, I don't think there's a size limit, but anyway, all of the cutouts are basically limited by the size of the patch and tract that are in the parent in the database remotely. So I think you can just retrieve that using this if you wanted to. All right, so now, so I mentioned earlier when we were in section 1 that we defined a little make image cutout function that would sort of wrap all of those things together so that you can just call the one function and it will do all these tasks for you and return the image cutout. So that's what I'm testing out here. So here we're gonna run make image cutout. So we have the tap service that we initiated earlier, the RAN deck of the Galaxy cluster center that we called. We have the data ID specifying the patch and tract and band of the image that we want to get a cutout of. This function wants to know which type of image it is. By default, it will just use deep coad. And then you specify the cutout size using the circle function. And so here we're specifying 0.005 degrees. So it's much smaller than the other one. And then you can see this little image cutout gets returned. So sometimes these cutouts are running a little bit slow. And I should mention that the reason that they're slow is because the cutout service by default writes the FITS file to like the access point that we have at the moment for the cutout service is to store the FITS file in your directory. And so the writing and reopening is what's a little bit slow with the cutout, but it's a lot faster than transferring the whole patch and tract over. I think in the future, there are plans to return like JPEGs and PNGs sort of on the fly rather than FITS files, but at the moment, that's what's available. So the PNGs and JPEGs will probably be a lot faster if you can just display them without storing them to the disk. Okay, so now I'm going to start with a little science application. So for my own research, I'm very interested in making cutouts of objects because it's very useful for validating when you select a sample of galaxies, for example. So I study galaxy evolution and primarily focus on high redshift galaxies. And so it's very useful to be able to visually inspect and validate whether or not the objects that you've selected really do look like the galaxies you're trying to find. So for high redshift galaxy identification in LSST, we're probably going to be making a lot of use of color selections. And so I'll talk a little bit about that. But color selections for galaxies also can have a large number of like contaminants in there. So things that look like galaxies but aren't actually galaxies. And so it's very useful to be able to see what they look like. So I'm going to use the example of a Lyman break color selection. And so I recognize probably some people are not high redshift galaxy experts in this audience. So I'm just going to sort of overview briefly what that means. So galaxies at very like cosmological distances from the Milky Way have a lot of foreground hydrogen that absorbs light from the galaxy. So what this looks like here, this is just a little schematic showing what that looks like. So this background here in black is the spectrum of a galaxy at a redshift of about 4 or so. These are transmission curves of filters that you can observe galaxies with, sort of similar to what we'll do with LSST. And as you go to high redshift, like this one at redshift 4, all of the light that is emitted blueward of hydrogen, Lyman alpha or the Lyman continuum gets absorbed by the intervening hydrogen gas. And this gives you a very strong determinant of the redshift because we know what the redshift of hydrogen absorption should be. And so we can determine what the redshift of the galaxy is. So here you can see the galaxy's light is absorbed in this blue filter, because it's at a redshift where all of the light is absorbed by the foreground hydrogen, and then you can see the galaxy in the redward filters. And so this is how we perform Lyman break selections. Here's just a fun little video that I found on YouTube that sort of shows this. So this is showing again a spectrum of a galaxy in gray with these different filters in colors, and then in the bottom panel you see cutouts from each of these filters. And so you can see that so what you're going to see in this video, I'm going to play it, and then the galaxy is going to move to higher and higher redshifts, and you'll see it progressively drop out of these filters in the bottom panel. So I'm just playing that, and so you can see the galaxy images in the bottom, and then the galaxy moves to higher and higher redshift, and you can see that the image of the galaxy drops out as it gets to higher and higher redshift based on what redshift it is, because all of the hydrogen in the foreground is absorbing the light from the galaxy. So this is sort of this is the principle of Lyman break color selection. So we're going to use DP 0.2 to select some Lyman break galaxies to identify candidates. Oh, sorry. Just replayed, continued playing new videos. Okay, sorry about that. All right, so sorry. So in DP 0.2, we do have high redshift galaxies in there. The high redshift galaxies ended about redshift of 3, but because we have a U band in the LSST filters, that means we can still select galaxies at redshift 3. That's about as high as you can go. So we're going to do this exercise and see if we can find some high redshift galaxies. So I just picked sort of a generic color selection for galaxies at redshift 3, which is this U band minus G color greater than G minus R plus 1, and G minus R less than 1.2. Don't worry about this. This is just, it's sort of a generic color selection. It's been written about in many different papers, and it's sort of not that important. But it does help us to figure out which of the galaxies in DP 0.2 might be high redshift galaxy candidates. So there's not a lot of high redshift galaxies in DP 0.2, so we're going to do a really large search radius of 4 degrees. And this is going to help us to collect a large number of Lyman break galaxies, because galaxies at high redshift are rare, and we're going to try to pick bright ones because we want to have nice cutouts. So we need a big search radius for this. So I've just defined some random location on the sky, a very large search radius, and we're going to look for galaxies that match these colors in this search query here. So I put in a few other specifications. We want very bright galaxies, so I specified that we want G band flux of brighter than 24.5, and we want high significance detection. So we've put signal to noise in the R band of greater than 10, and also in the G band. So now I'm not going to run this query. It takes a minute, but the query's already returned here, but this may take you a few minutes to run, or a few seconds. It looks like 18 seconds. And it returns a number of galaxies that match the colors that look like these redshift 3 candidates. So there's a whole bunch of them. They're all stored here in this table. And then we want to go and sort of figure out which ones are the most optimal. So actually, but before I do that, I'm just going to give you a visualization of what this color selection looks like. So this is the U minus G color and the G minus R color. And very strong U minus G color represents this big drop off in flux where the hydrogen is absorbing the starlight, and indicating the galaxies are at redshift around 3. So you can see these are very different from the rest of this. The blue is showing all objects we returned in that query in that 4 square degree area. And you can see that these orange objects that are the Lyman break galaxy candidates at redshift 3 will have very different colors from basically everything else in the field. So that's nice. We're going to go make cutouts of these orange points and see what they look like and whether or not we think they're legitimate Lyman break galaxy candidates. So one thing to note is that sometimes this box will be filled with lots of contaminants, and so that's what we're trying to do the visual inspection to remove. Oh, there's a question in the chat. What are the limits on retrieved size you mean in the query, or in the search query in the catalogs, or in the image size?
Yumi basically asked exactly the same question. I just asked it in chat, so it's from the previous section.
Oh, sorry. Okay. Sorry, I missed the, okay, thank you.
No worries.
Okay, so just to help us, since this is a simulation and we have all of the sort of truth information about these galaxies, I also am including a little search here when we do the cutout print to help us to know whether or not these are real high redshift galaxies. But what I'm going to do is I'm going to plot cutouts in each filter for each of these orange Lyman break galaxy candidates. And then I'm going to search the truth tables to retrieve the actual redshift in the simulation of the object. And that's going to sort of, or it's sort of cheating, but since it's a simulation, we can do that and we can see which ones are legitimate, which ones aren't. So this cell takes a long time to run. So you can start it running, but it may take you 5 minutes or so. I already have the result printed, so I'm just going to show you the result. So if you're interested more in truth tables, we do have a tutorial about truth tables that you can go and access somewhere else. I forget the number. Oh, tutorial 8 is on truth tables. So I'm picking a query from the tutorial 8 truth tables. I'm retrieving the redshift. Let's see, so I'm retrieving the redshift here from the truth table for each of these Lyman break galaxy candidates, and I'm plotting all of the cutouts. But actually, I didn't do all of them because it takes a long time to plot them because you have to call the cutout tool, save the FITS file, and then open the FITS file to make the image. So it takes a little bit of time. So I'm just showing 5 examples here. So these are our Lyman break galaxy candidates. So the filters are, I have a cutout of the U band, the G band, R, I, and Z. And next to the filter name, I'm showing the matched redshift from the truth table. So you can see that most of these things that we picked out are about redshift of 3, which is great. So they're like 2.9, 2.9, 2.9, because the simulation cuts off at redshift 3. So we're all going to have like things very close to redshift 3. And then you can see one example of why you need to make these cutouts for visualization purposes, which is that we have an interloper at redshift 2. And you can see it's an interloper because there's flux coming in the U band where we know that if it's at redshift 3, hydrogen should have absorbed all of the light from this cutout, from this image, sorry, from this galaxy. And so this is something that I think, from the high redshift galaxy perspective is a useful science application of the cutout tool, because you can understand what fraction of your sources are interlopers and which ones are sort of legitimate targets that you're interested in. So I'm sure there's other applications from other science subfields as well, but this was just one that I thought was interesting. Okay, so now I'm going to go to focus on CalExp files. Up until this point, we've been just using the cutout service for deep coads. Actually, since I'm changing sections, are there any other questions on that one little science demo and running the cutout tool, or anything else, I guess?
I had a general question.
Yeah.
How is the tract ID determined?
So the tract ID we queried for the patch and tract that contains the RA and DEC. Let's see, back in section 2, there was a query that we did to the is it this one? Yeah. So we did a query to the ivoa.obscore catalog, which contains it gives you it returns the yeah, it returns the patch and tract that contains the RA and DEC.
That makes sense. I guess I was just wondering, like, where does the number itself come from? Is it related to the RA and DEC?
Oh, I don't think so. I think I mean, it might be in that some of them are sequential with each other. So there's a definition for the whole southern sky that we intend to map with LSST. Each part of the sky has a predefined number for its patch and tract. I don't know how they came up with that specific grid of patch and tract IDs. Maybe somebody on the call knows the answer to this question.
Yeah, I think like you said, it's just like tiling the sky with tracts. I think it goes along right ascension maybe and rows along right ascension. It's sequential, but yeah, the tract is the number has no relation to the sky coordinates. It's just a fixed number based on how the sky was tiled.
Okay, thank you guys.
Let's see. Okay. All right, so to date, we've been using, or sorry, up until now, I've been talking about making cutouts for deep coads, but you can also make cutouts for calyx files. And you have to specify the data ID in a slightly different way, but there's still, that data is stored on the remote database, and there's still a data link that allows you to access the location. And the cutout tool will still make cutouts of calyx files also. So I'm going to demonstrate how that works. And we're going to use an example of a transient and how and retrieving cutouts of a transient object around a transient event in order to see visualize how the transient is changing in flux and to confirm its variability. So we're going to start with a known DIA object from an earlier tutorial notebook, tutorial notebook 07A. So we're going to retrieve we know the ID from the earlier notebook, so we're going to do a search for the RA and DEC, the flux, and also the time over which this, I think the time when the transient event for this object was detected in the DIA source, or the DIA object and DIA source catalogs. So here I'm running a query to use the data, the DIA object ID from the DIA source. So we're going to get all transient events associated with this specific object and the RA and DEC of those transient events. So I do that query, and we save those transient events from the DIA source table in this table here. So you can see we got something like 9 DIA events, meaning that the flux of this object changed enough to be flagged by the difference imaging. And so now we want to plot all of those DIA sources, or all of the transient events, and we want to plot the calyx images so that we can compare them from one exposure to the other to see how the flux is changing. So here I'm just going to specify, again, the RA DEC from the table that we did the query of. I have just some image scaling parameters so that we can make this cutout. And then I'm going to call, so I'm going to, and oh yeah, in this search result, we also grabbed the midpoint time when the transient occurred, or at least the difference imaging, the difference between the two difference imaging, and then also which CCD visit ID it came from, so that we can retrieve the calyx, or so that we can retrieve the so we can retrieve the right calyx where the transient occurred. So here I'm going to define the data ID for the calyx file, which is based on the visit and the detector. And then I'm going to send these to our little function make image cutout. In this case, I'm now specifying, so like before, I specify the tap service, the RA and DEC of the source, and then the cutout size, but now I'm specifying calyx, and that gives the little function information that it needs to read the data ID in terms of the calyx data ID parameters, not the deep coad ones. So again, this function just finds the data link to the image and then sends the cutout service your cutout parameters, and will save this file as cutout underscore number.fits. And so we're going to iterate over all of the DIA source detections that we had. So this is every time that the flux of this object changed, and we're going to save a little cutout for that image. So here at the bottom, you can see, also I made so each of these cutouts shows one of the calyx images when that object changed flux. And you can see the little text there is showing how far since the first transient event, how long in time since the first transient event it occurred. So we've sorted them in terms of time since initial event. So you can see the object here and you in the middle of each of the objects, and you can see that it's sort of hard to see what's going on. It does seem to get fainter, but the scaling of this image is based on also the brightness of all the other objects in the cutout. And you may notice that the orientation of the images with respect to north is changing. So you can see that because of this bright neighbor, it's always sort of facing a different direction around that. And that's because the CalExp files don't always point north the way that the deep coads always point north. So that means if you want to compare the same field, you're going to have to change the orientation of the images so that they all align with each other. So we're going to do that so that it's easier for us to see what's going on. So we're going to use this, we're going to define the reference cutout, which is the first one, the first time that we detected that flux was changing in this object. We're going to define that as the reference cutout, and then we're going to change the image orientation of all of the subsequent images to match the same one as the earlier one. So that's what this get minmax xy function that I showed you earlier, but we sort of skipped over. That's sort of what that's doing on the back end. So we're going to run that so that we can see what these images look like when they're all sort of rotated. So I should also mention that in order to rotate them, you also need to sort of warp and resample the pixels because the CalExp files are all sort of in different orientations. And so that's what this warp image file or function from earlier is also doing. So don't worry about the details of those, but that does allow us to now plot the transient images all in the same coordinate system. So now you can see the bright neighbors on the top, and now it's a lot easier to see that the image in the center is getting fainter and fainter towards the end of the transient event. And so just in the last 2 minutes, we also have this other function called make GIF that will stitch together all of those images in a little video. So I don't know if you caught it. I'll bring it back down here. Oh, actually, it's not allowing me to play it again. Okay, hang on. Oops, and now it's not working. Okay, hold on. Let me just go to where it is, so that you can see it. Where did it go? Oh, it's not there anymore. Okay. Hang on. Okay, sorry. Let me, I think the images get deleted at the end, and so I need to go back and make these. I need to run this cell again. Sorry about that. Bear with me for 1 second.
It's worth the wait. Oh, cool. It's worth the wait.
Thanks, Tina. Also, kudos to Jeff and Ryan for figuring out how to do the making GIF function. Yes. Question from Becky.
Hi. So I actually came here because I wanted to hear about the cutout service, and I didn't realize you would have a cool example of actually aligning the CalExp images, which is something I've also struggled with for a while. In these images, like you're not plotting the coordinate systems, but if you were to plot the WCS coordinate systems, are they also aligned with one another from one image to the next?
No, all of the CalExp files have their own WCS.
Right.
So, but that's partly what, so Jeff, do you know if the function that we're using here retains the WCS information? Because there would be a way to do it, but it might mean you'd have to alter the function.
I think that function is just taking the first image, or it's sorry. For each image, you use the WCS from the CalExp, and basically the warp just says, warp this given image to the first image from the list, and it does that using the WCS. So then at that point, they should all be on the shared WCS of the first image from the list, if that makes sense.
Yeah, that does. Thank you.
All right, I think it's almost done. Oh, taking a long time. Okay, all right, so now I'll run this little animation so people who missed it can see it, and I will not delete the files. So here you can see it, just the GIF just stitches all the images together so you can kind of better visually see the brightening and the dimming. So yeah, so that's the end of the tutorial, and I'm happy to answer any questions that may have popped up in the meantime. Becky.
Okay, so the reason I came to this tutorial is that I'm curious about using the cutout service. Because for the citizen science team, we're trying to send like 10,000 images to Zooniverse. And it's just like really, really slow and uses up a ton of memory to use. We're building off of one of the earlier tutorial notebook examples where you have to deal with the whole like patch and tract and everything. So I feel like this would be a good alternative for that reason, because you don't have to deal with all the extra info we don't actually need. But I'm wondering about, we're trying to like tweak it in a way that's parallelized. And so I'm wondering if this is like a thread safe service at the moment, or if you're thinking you would need to like do more things to it to make it run efficiently in parallel.
I haven't tested that out, and I also haven't tested out using the like parallelization on the Rubin Science platform at all, but I think that we recently had a question about this, and I think it is possible to do. And so all of these cutouts, I think, are individually independent from each other. So I think you could launch many of them at the same time with different on different threads or whatever. Is that what you were? So they would, I don't think they're going to conflict with each other or depend on each other in some way that you can't parallelize this. Having not tested this out at all, but if someone else on the call knows more about parallelization, please chime in.
Yeah, I'll say that I also am not running the test for this. This is all Eric Rosa's. And he was saying that there's also an issue with Matplotlib, and it was not thread safe, which kind of shocks me to my core, honestly. But it sounds like Matplotlib actually put up some changes that made that thread safe. So as long as like the service itself is, I think we can maybe move forward with sending a bunch of parallelized images at once. But maybe we'll be in contact with you more about this as we like move forward with testing.
I think actually, so he did ask me a question on Slack about that. And I didn't immediately know the answer, but I think we hooked him up with somebody that did. And so I think he's testing out the proposed solution. And so maybe that means we didn't hear back from him. So maybe it worked. I don't know.
I think he's still testing. So
Okay, all right.
Okay,
Well,
cool.
keep us informed, or I think we're very interested to know user experience with this, and
Yeah.
so
If it works, that would be great. I mean, it is a big data survey, and we are going to have to send a bunch of images to Zooniverse. So that would be awesome.
yeah,
Cool. Thank you.
sure. Tim.
Hi, Christina. Thank you for the talk. My question is, do the cutouts have to be aligned with RA and DEC? And what we would like to do for comets is I'd like to cut out a rectangle that goes along where the tail might be.
Oh, yeah, that's a good question. I haven't successfully made a cutout that's not a rectangle with north up. It might be that this is an application that we want to have at some point, but I don't actually know the answer to that, or whether or not there's like a plan to do it.
I'll leave it with the team then, shall we say?
Yeah, I mean, one thing you could do, I think that would be useful is to put your question on the community forum, because there are a lot of people that are working on the development of the pipelines and the sort of software infrastructure that would be interested to know and may have a better idea how to solve this problem than I do.
Yeah, that's a good idea. I'll do that. Thank you.
Sure. Are there any other questions or unrelated questions to this that people want to ask the community science team?
I have one that I've asked before. Exposure F. I don't know what exposure F means, and I don't know if there's an exposure A, B, C, or D. I see it and I just wonder every time.
Yeah, so I think it stands for exposure file. And so it contains a bunch of metadata along with the image that is useful for various Rubin Science Platform pipelines functions. So it's not, so I don't know, someone maybe who knows more about this file type should continue with the question. That's the
Actually,
end of it.
yeah, I think the F is for float, meaning that
Oh.
all of the pixel values are floating point values. And so there are, and so yeah, and as Christina was saying, that exposure is just, it's a type of object defined by the pipelines, and so it carries along a lot of attributes, like you've seen, you know, the WCS and the photometric calibration object, and all of those things are part of the exposure F object. And the F just means that it's stored, that its pixel values are floating point values. I think in theory anyway, there could be an exposure I that has integers, and an exposure D that has double values and stuff.
So kind of a meta file for the image.
Yeah, it's kind of like it's like a container that brings along the image and a lot of associated things that you need to work with that image.
Thank you.
Mm-hmm.
This was fun. Thank you.
Okay, great. Yeah, if there's no other questions, I guess we can end a few minutes early.
Thanks, Christina. That was really good.
Yeah, thanks for coming, everyone. This was great.
Yep, thank you.